topic. Today we're going to have a look at parametric equations. Normally we have equations which are x and y. This time x equals something like t and y equals something like t. And so we can describe something with more than one equation. And what we can then do is try and tidy the two together and make them work out properly. Let's have a look at these. So I might have a curve and it's described by something like x equals 2t. And we might have another way of describing it and say y is going to be something like t squared. And we're going to look at this in the range from -3 to +3, and that is the value of t. And we're asked to perhaps find what is a Cartesian coordinate. So our first job is to try and get this in form of t equals. So we rearrange the equation so that I can say that t here is going to be x over 2. Now if I know that, and I know that y is t squared, then I could say that y equals x over 2 all squared. And that's going to give me y equals x squared over 4. And that is my equation, my Cartesian equation from a parametric equation. Now, when we look at these things, it's a good idea to have some idea of what the basic sort of domain and range of this is going to be. Basically, the domain of this function is the range of the parametric function of x. So the range of x equals 2t over this domain of -3 to +3 is going to be twice those numbers. So it's going to be from here -6, and this time it's going to be x2 plus 6. So we've got our domain. We also need to work out the range. The range of the function is the range of the parametric function for y. So we've got here something like y is t squared. Now that can equal 0. So what we can do is we can look at this and see, well, what's it going to be? So it's going to be the square of those. So basically it's going to come down from 0, its minimum value, which it can be equal to y, and its largest value will be here, this squared, which will be 9. So we've got an idea of what that looks like, and then can I try to sort of work out a graph? Well, the easiest way of trying to draw this graph out, it's going to be y equals, we've got here basically it's going to be 1/4 x squared, and so we can try to work out what that's going to be. So if I take my little sketch, and this is easier sometimes to do this on a graphical calculator, and we can just call up a graphical calculator so we can sort of get an idea of doing this, but we don't have to. And this is going to be when x is going to equal 2t and y is going to equal t squared. So we've said what it's going to be. I know it's going to go through 0. Y will be 9 at the value 6. So we've got minus 6 to plus 6, and we know that's going to be the value of 9 there, right in the middle of where I've drawn it. And this is going to be an x squared. So we're looking for a graph that looks something like that. It should be asymmetric. Sorry, it should be symmetric minus asymmetric. Let's have a look at a different one. Now, we might not get something that's going to be rather nice, but we might get something that's going to be particularly not nice, and we might have all sorts of nasties. And an example of this would be x equals then the ln log to the base n of t plus 3, and I might be told that y is 1 over t plus 5. So if we've got something like this and we're asked to find the Cartesian coordinates of this, well, again, what we've got to do is we've got to find out what this is in terms of t. The ln is going to give us a problem, so let's get rid of this, and I could say that e to the x is going to equal here t plus 3, and therefore we can work out that t is going to be e to the x minus 3. What else can we try and do here? Well, we can now substitute this into there, and I can say that y is going to equal 1 over e to the x minus 3 plus 5, and that's going to give me 1 over e to the x plus 2. Well, where do we go from here? Well, once we've got this sort of idea, then we can sort of move on and look at perhaps our whatever we want to look at, domain, range, fairly standard sort of things to sort of have a look at. So let's see what we might have here in a particular range, and we might be told here that t here is greater than minus 2. So if we know that, then if I say that t is going to equal minus 2, what we're going to get? So what will x be in that case? Well, x is going to be log to the base n of minus 2 plus 3. Which gives me the ln of 1, and we know that the ln of 1 equals 0. So we can now take some ideas that as t increases, so the range of this will also increase. We've got our Cartesian equation, y equals 1 over e to the x plus 2, and so we can see this is going to be valid while x is greater than 0. So we've got an idea of the range of our values. What else can we see Well, we know that when here t is minus 2, then y is going to equal, in this case, looking at the original equation, 1/3. As t increases, y is going to decrease, but it remains positive. So we can say that here 0's got to be less than y, which is going to be less than 1/3. So we've got here some simple ways of trying to solve some problems. We're just basically making one thing more or less equals something else, and it makes it sort of relatively easy to try and do this. Now let's go and try and choose a question where we can sort of apply this. So we'll just choose some sort of question and see if we can solve some sort of parametric equation this way. So let's choose some sort of question and get started. I've got an equation, let's say we've got to find something for. I've got x equals 2t squared minus 3, and I'm told that y equals 9 minus t squared, and we're told that t is greater than 0. Alright, so there's our equation, and what we want to do is we want to try and work out, first of all, the Cartesian equations for this. Right, so where are we going to start? Well, let's rearrange this. So I can say that x minus 3 equals 2t squared. I can say that x minus 3 divided by 2 equals t squared, and therefore t equals plus or minus the square root of x minus 3 over 2. Now, I'm told t is greater than 0, so in fact I'm only going to need to take the positive root. So let's substitute this now into there. So we've got y equals 9 minus the square root of x minus 3 over 2 squared. So this is going to give me y equals 9 minus x plus 3, x minus 3 that was minus 3, that's got to be plus 3. Yeah, I was right. X plus 3 over 2. And let's see what we've got. So to work that out, that's going to give me 9 over 2, which is going to give me 18 minus x minus 3 all over 2, which is going to give me 15 minus x over 2. So my equation, I'd probably write that out a little bit better and say the Cartesian equation is going to be y equals 15 over 2. I could put 7.5 if I preferred, minus a half x. And there's my Cartesian equation. What's the domain? What's the range? Let's have a look. Well, if we look at our original equation, we've got x is 2t squared minus 3. This is a quadratic, and I can look at this quadratic and I can say it's got a minimum of minus 3 at t equals 0. So the range of this parametric function has got to go where x is going to be greater than something like minus 3. Let's have a look at y. I'm told that y equals 9 minus t squared when t is greater than 0. This too is a quadratic function, and will have, in this case, a maximum value of 9 when t equals 0. So the range here of this parametric function is that y has got to be less than 9. And then sketch this curve, straight line, whatever it's going to be. Well, let's see what we know. We know that we've got an equation which is y equals 15 over 2 minus a half x. So I've got this at about minus a half x. It's going to go through something like that. That will be at 15. And what do we know for this? Well, I know that at the position minus 3, then this will be at minus 3, 9. So we've got enough to try and graph our equation. So there's going through some sort of problem that I just chose at random from a book. How about trig? What can we do about trig functions? Well, they're bound to throw them in with parametrics to make life fun, and they certainly do make life fun, don't they? So let's choose something to say that perhaps x is going to equal sine t plus 2. I'm told that y equals cos t minus 3, where we're told that t is some sort of real number. And let's see if we can do anything. Right, so what can we get from this? Well, first of all, I need to try and work out what t is. I can work out what sine t is. I can say that sine t here equals x minus 2. We can also say that y here is going to be simply well, we've got cos t minus 3. I want to get in form of, so we can say that cos t here equals y plus 3, and we've put those together. Let's put them together and see what we get. Now, what do we know to try and join these two together? Well, I know that sine squared t plus cos squared t is equivalent to 1. I know that sine squared t is going to be x minus 2 all squared plus y minus y plus 3 all squared, and that's going to be equal to 1. And that I can look at and say that is going to be, in fact, the equation of a circle. How could I do that one? Well, probably one of the easiest ways of doing that is to cheat and use the calculator. And it happens that I've got one of these calculators, and let's just make it a little bit better. I hadn't set my thing to normal, so I'm just going to set that to normal, and I'm going to set my calc screen to normal. Then you can see it properly a little bit easier. And what I want to do is I want to draw a graph, and my graph is going to be, I like how this calculator remembers what I was doing, so we're just going to have to delete, and I'm going to put in here my brackets of x minus 2 squared, and then that's going to be plus my other function, which is y plus 3, and here I'm going to have to choose y. That may not be what I wanted. All squared, and that simply here is going to equal 1, and that gives me a little bit of grief, but we'll try it. Yeah, I thought so. I can go back and edit that one. See if we can cope with this. I think it's not got my correct y in there. That's my problem. Okay. Not going to spend time playing with a calculator doing that. I would just have a look at this. I know that this is going to have the coordinates of 2 and minus 3, so we go across to 2, we go across to minus 3. There's going to be my center of my circle, and it's going to have a radius of 1, so I'm going to have something like that. where this point here simply is 2 minus 3, and we've got that at 1. Sometimes it doesn't work out quicker using the calculator. Sometimes it's just as easy to sort of do these things without. So that gives us some sort of basic sort of equation to do things, and you can see that it doesn't really matter if we're trying to do something parametric with trig or not. They're not really that difficult to try and put in. Parametrics are always done in the same basic way, that we look at something and then we turn it into the values of t equals, and then we can join the two equations together. So we've got this idea of playing around with trig functions and trying to do the curve sketching. We can use a calculator to save us a lot of the time, or if we need to, we can do it the old-fashioned way. Trying to do some of this the old-fashioned way is we've got something like a particular equation that might be x equals 3 cos t plus 4, and I've got y equals 2 sine t, and we're told it's anywhere between 0 and 2 pi. Now what we've got to do is try and work out what the Cartesian equation is for this, and we need to sort of go ahead and work out what that is. So let's see if we can work out what this is going to be. So this is going to be x minus 4 equals 3 cos t, and I've got my x minus 4 over 3 equals the cos of t. Let's do the same for this one. So we know here this one is simply, it's going to be basically y over 2 equals the sine of t. I know from my work that sine squared t plus cos squared t equals 1. So let's substitute into there, exactly the same as we did before, and so I've now got x minus 4 over 3 squared plus the other equation, which is y over 2 all squared, and that equals 1. So there is my equation. This is in fact here a little sort of circle type of shape, and what we could do is we would work this all out, but we could work out, if we wanted to, a table of values for this, of working out what we're doing. So we can put in various different values of t if we want to, and we can plot those to try and do this. Let's work out from this what we've got. So let's work out a table of values. Now the table of values we can work out with a calculator, or we can just try and do these in an approximate way. I'm going to look at some values. Let's look at 0. Then we could look at things like perhaps pi over 4. We could look at pi over 2. I could look at 3 pi over 4, and I could look at pi, and then we could look at 5 pi over 4, 3 pi over 2, 7 pi over 4, and finally 2 pi. Being able to sit down and just go through those is something that you need to be able to do. And what we could do is we could work out each of these values for both x, and we know that x is 3 cos t plus 4, and we can do our y value, which is 2 sine t. Let's look at what we've got. Right, at 0, then the cos of 0 is 1. 1 times 3 is 3. 3 plus 4 makes 7. At 0, the sine of that's going to be 0, and anything times 0 is going to give me 0. And I'm quite proud I can sit down and do that one. But trying to do some of the others becomes a little bit more difficult. I might be able to manage this one, pi over 2, and pi over 2, we know that's going to be half, so that's going to give me 4, and here sine 2t is going to give me 2. This is going to give me 1 and 0. This one's easy. This one's going to give me 4 and minus 2, and I've got 7 and 0 again. Now if I want to go and put in some of these extra points, then I certainly can go along and use the calculator to do this.
I'm reminding you, take up written tablets.
Now if I'm going to try and draw this, then a quick sketch of this, not going to be too difficult. What we want is our graph, we've got our y values, and our y values here are basically going to go up to 2, and they're going to go down there, and then across the values are going to go from about 1 to 7, and I've got 4. So if I put in my values of, we've got 0 and 1, I've got 0 and 7, I've got these values, then in fact if I try to draw this, I can see that this is going to be in fact something like one of these ellipses. I don't have one the right sort of size for this, so we'll just make our own up. And how awful is that? But basically this is going to be some sort of ellipse. In the exam, if you've plotted all the right points and you've got all those done, then if your graph doesn't look quite right, then you've made your best attempt at trying to do this. So we've got these ideas of trying to sketch curves and try and do various bits and pieces with these. Now we can do more with these parametrics, but one of the things that I want to try and do is, rather than go on with some of those things, is to see if we could actually differentiate one of these parametric equations. So we know that we're given some sort of functions when we want to do this. We want to do dy by dx, but we've got these things given out slightly differently. So I can say that t is going to be dy by dx, but that's actually going to be dy by dt all over dx by dt. And this is our parametric. We get this actually from working out basically the standard shape rule, and we get that by working out that something like dy by dx times dx by dt would actually give me here dy by dt. So let's suppose we're asked to find something like the gradient and that's what differentiation is all about. The gradient at t equals 2 for the equation where x equals t cubed plus t and y equals t squared plus 1. Where do we start? Well, let's work out what dx by dt is, and that's going to be 3t squared here plus 1. And we can work out what dy by dt is, and that's going to be 2t. Now let's put this into this formula. So I can say that dy by dx is going to be dy by dt, which is going to be 2t, all over dx by dt, which is 3t squared plus 1. So there is my gradient, and we're told that when here t equals 2, so we've got simply when t equals 2, we can substitute in there for t. Let's do that. So that's going to give me 4. We've got 2 squared, which is 4. 4 3s are 12 plus 1 makes 13. So my gradient at whatever point it was is that. So we can do these sort of things quite easily. Now let's just have a bit of fun with this, and we'll try something a little bit nastier, and we'll try one of these with cos and sine in there, and that's not that difficult. We'll just go for a sharp pencil for a minute, and we'll choose another equation. So this equation, let's just choose something, and we'll try x here is 3 times the sine of theta, and y equals 5 cos theta. And we're going to try and find the equation of the normal at the point P where theta equals pi over 6, and we're going to try and find here equation of the normal. Okay, so what do we know when we start? Well, we've got our equation here. Let's work out what dx by d theta is going to be, and dx by d theta is going to be 3 cos theta. dy by d theta is going to be minus sine, so that's going to be minus 5 sine theta. I know that dy by dx equals dy by d theta all over dx by d theta. So let's put those in. So we've simply got there minus 5 sine theta all over 3 cos theta. Now we're going to try and work out the equation at the point where this is done. So we've got this point. So let's put these in. So when we've got that, we've then got minus 5 times the sine of pi over 6, and the sine of pi over 6 simply here is going to be a half, and I've got 3 times pi over 6 cos of that, which is going to be root 3 over 2. So I've got trying to work out the easiest way of trying to do this. That's 3 root 3 over 2, but that's about a half, so 2 is going to cancel, so it's going to give me minus 5 over 3 root 3. So I've got my little point there. We're asked to try and work out the equation of the normal. So I know my gradient. We know then we've got this at point, I know, some point P. So at P, x is going to equal 3 over 2, and y is going to equal 5 root 3 over 2. So our equation for our normal is going to be y minus 5 root 3 over 2 equals my gradient, which is the normal. It's going to be the negative reciprocal, which is going to be 3 root 3 over 5 times x minus 3 over 2. And if we multiply the 5 over that side, so I'm going to say that 5y equals 3 root 3x plus 8 root 3. And it gives us our differential and our gradient, and we also get all caught up everything else. So we've got, there we are, an idea of parametric differentiation. And I've tried a couple there, one with signs and one without, and we can also get other nasties in there. And usually when I do this, someone says, well, could you not just do one of these with something horrible in there? And I say, well, okay, let's just try one of these with something fairly horrible in there. And so let's think of something. And let's choose something with something nasty. How about x equals sec t and y equals tan t. Let's go and have a look at something like this and see what we can actually do with one of these. Right, so where are we going to start from here? Well, probably the sensible place to start is just trying to get these sorted out into something that's a little bit sort of easier to have a look at. So let's differentiate this. So dx by dt, differential of sec is going to be sec t tan t. The differential dy by dt here of this is going to be sec squared t. Let's put them together. Dy by dx is going to be dy by dt all over dx by dt. And I would strongly advise trying to write this down so someone can immediately see what you're doing. And that's going to be sec squared t over sec t tan t. The secs are going to go, so I'm going to end up with sec over tan, and I've got to work out what that's going to be. So that's going to be sec, we know, is 1 over cos, and I'm going to then divide that by tan, which is sine over cos, which is then going to be multiplied by cos over sine. They're going to cancel. I'm going to be left with 1 over sine t, which is cosec. Some people just write that to that. I find if you go through all the extra stages, then everyone seems to understand exactly what you're doing. So there we are, some parametric equations, trying to fix them, sketch them, work out their domains, work out their ranges, and then trying to work out how to differentiate them. And really not that difficult as long as you can remember that formula. Hope you found this useful. If you did, then like and subscribe, and I will see you next week when we do some more A-level maths, topic by topic. Until then, take care. Bye bye.